and this lecture will be about statistics. So this is your first video lecture, and today we are going to be covering the statistics. So simply, define data, define mean, median, mode, standard deviation, and standard error, a bunch of different ways of measuring a population. Best give examples for when to use each one of these statistical terms. So if I say, when would you use a median? You give me an example when a median would be appropriate. Be able to calculate all of these statistical terms, although to be honest, standard deviation is going to be a few labs hence. And use Microsoft Excel to calculate all of these. This will be the homework. So why are we looking at statistics? Well, it's good to have a feel for a population. It's better to just have numbers for a population if we are communicating information about that population to another. So statistics in general, it's a scary term that just means how we're making sense of the data. Although if I were to say I'm going to teach statistics, people would say, oh crud, it's math time. Yes, it is math time, but this is not an oh crud moment. This is a good opportunity. So the data is just some way of saying a collection of facts, a collection of numbers, observations, some sort of informational way. The singular point is just a datum. So data is plural. Let's talk about data, which is going to be that guy from Star Trek, which he's singular. So anyway, an experiment, we should know this. It's a way of verifying information, testing a hypothesis, manipulating some variables, etc. This is earlier classes. And what is a hypothesis? Well, it's a testable, falsifiable kind of explanation why we think something happens. Let's talk about the different types of statistics. First up would be descriptive. Descriptive statistics are how we're going to organize or summarize the data. So the mean, the median, the mode, and such other. So these are three terms about kind of the average, general. Mean is a numerical average. Median is a smallest to largest middle, and a mode is the most common. There are also terms such as standard deviation, abbreviated here as STDEV, and standard error. So these are different terms that can give us a description of what the population looks like. So we're going to compare that to inferential statistics. Inferential statistics are not telling the whole data story. They're generalizing from a sample to a population. Inferential statistics as well are going to be about testing your hypothesis. So statistical tests are a form of inferential statistics, saying this sample from this population represents it, this sample from this population represents that, and then we're going to compare the two using a sort of test. So the mean, the median, and the mode are different methods of getting a feel for the population, whether it be the average, the middle, or the most common. And here, enjoy this little video of me in the garden talking about mean and median and mode. How is the garden doing? A simple question, and a general answer would be, it's doing very well. But that's not a very scientific answer, and this is a science class. So how is the garden doing? Well, I could answer that by actually measuring every single carrot and saying, all right, so we've got a non-metric ruler here. Can't use that. But let's say every carrot was measured, and I presented that huge hunk of raw data to you. Well, that's a very scientific measurement, but it's not very useful. So how do we make a scientific and useful observation about the simple question, how is the garden doing? What I can do is I can take different measurements of the population of the garden. So let's take, for example, we've got a couple plants here. I've got buckwheat, which is not for crop use. It's just bees and nitrogen. and we've got carrots. Those carrots are going to be a primary staple of my my diet. So how is the garden doing in terms of carrots? Well, my carrot population goes from butternut squash all the way over to Tomato Town over there. So I can measure my carrot population. And what I would do for that is I would take a sample out of that population. It is not very efficient to just take every single carrot and measure its height because, well, there are a lot. So that's not a very scientific or efficient method. If I want a nice efficient method, I'll take a subsample of my population. So say I take 25 carrots and I were to measure the height of each of them. So that would give me, if I took that, all those heights, added them up, and then divided it by the total number of carrots measured, 25 in this case, that would give me a mean. So that's the numerical average of a sample from the population. Well, let's say I took those 25 carrots and I lined them up, and the one that fell 13th from the smallest and 13th from the tallest, that's the middle carrot right there. The middle height is going to be my median, which is another useful statistic saying the median height of carrots is, well, 8.5 inches. Okay, probably should put that in centimeters, one of these statistics. But anyway, but let's say I took the carrots and I took what is the most common height. The most common height is, say, 20 centimeters tall. That most common height is the modal number. And given that most of these carrots were planted around the same time, germinated around the same time, and given the same amount of delightful air and sunlight, they're probably all going to have a relatively similar mode. So they're going to be about the same height. The modal height is probably going to be it's going to be pretty close to the mean. So when the modal height, the most common height, is close to the mean height, the average height, and close to the median height, which is that one sitting in the middle, we would then say that it is a normal distribution. And from a normal distribution, it's easy to get a relatively good sample. The most common carrot that I'm going to pick is probably going to be about representative. So normal distribution is going to be giving us a pretty reliable small sample, is going to be relatively equal to the population. What we could also measure is how variable that population is. I said that they should be about the same height, but some of them are growing underneath a buckwheat plant. It doesn't actually affect them that much, but it might a little. They might be a little shorter because of that. And that may cause some variation in there. How variable the population is can be measured by the standard deviation. So how much, on average, does a carrot vary from the average? That's going to be your standard deviation. We also have the standard error, which is the standard deviation divided by the number of samples, the square root of the number of samples. So if I took 25 samples and I have a standard deviation of 5 centimeters, I would take that 5 centimeters and I would divide it by the square root of the number of samples. So 5 divided by the square root of 25. So 5 divided by 5, my standard deviation of 5 becomes a standard error of 1. Standard error is always smaller than standard deviation. So there you have it. You have a population of carrots. We would take a sample from that population and we would say what the mean, median, or mode is of that population, and then we would have the standard error or standard deviation to say how much variation exists within that population. We can answer the question, how is your garden doing, with a numerical quantity and a certain amount of variation. Looks good. Statistics and data. Let's look about some other ways of handling the data with statistics. So if I were interested in presenting, analyzing, and organizing some data, let's take a question. Who watches Tiger King? I do. I loved it. It's all villains and animals and beasts and eating people. So cool. But who in general watches Tiger King? What can we say about the population that watches Tiger King? How much Tiger King are they watching? Is there some sort of correlation between the people who watch all 7 episodes plus the 8th bonus episode and higher or lower IQ? Are people who watch it smarter than people who don't? These are all different questions which are answered by a whole bevy of descriptive and inferential statistics. So first thing we would need to do is gather data. And we want to determine what type of data we're going to gather. be it quantitative, so some sort of number like IQ, or qualitative, which would be some sort of non-numerical value, like maybe primarily redheads or primarily people with mullets are going to be watching this. Is it categorical or numerical? So are we measuring an age, which is a number, or are we measuring a category like baby boomers versus Gen Xers? Is it discrete or continuous? So discrete doesn't mean you just watch it in secret. It means you put it in small boxes, whereas continuous is going to be along a continuum, a gradient or such. So there's a method we collect this data. Are we going to measure the whole population, or are we going to just pick a sample from the population? Are our sampling methods going to be just a generalized survey, or are they going to be plumbing the depths of Netflix's data collection? What kind of errors might we make in sampling each different way? So maybe some people watch on someone else's account. That may lead to some sampling errors. Maybe some people got together for some Netflix and don't get ill because we're staying social distance, and they're going to be watching it together, so we're not counting all of them. All these different errors depend on their sampling method, which depends on whether we're doing a full population or just a sample. So let's look at some potential data. We've got here an example of categorical data. It could be, is it more males or more females? If you wanted to put people in those discrete category of male or female, it becomes categories. What is your age category? As I said, you're putting them in boxes. And this box kind of approach is a discrete approach. Employment, are they fully employed, partially employed, recently unemployed people watching Tiger King? So these are different categories we can fit them in. And the numerical value we're putting is the number that are in each kind of category. We could also mention the numerical value of, continuous age. So that'd be a different type of continuous numerical value, but numerical is going to be a number. We can present data in a bunch of different ways. So data presentation is really how we explain what we're seeing to someone else. We always want to make it more clear. So never just throw raw data at someone. I went to the website for some sort of statistics I wanted to get on coronavirus from Texas, and it was just a huge spreadsheet, just raw data. That's not how we present data in sciences. We're going to measure different types of, proportions or percentages, the frequencies. What is that going to mean? A proportion between 0 and 1. So perhaps we have this proportion watching here. Proportion watching under age 15 is 0.04. Okay, not many under 15-year-olds watching this R-rated show. Good. The highest proportion appears to be in the 20 to 25 age category. See, category, it's a numerical value, a continuous numerical value. Proportion watching is about 0.4. We could also say it's 40%. So the percentage is going to be a value between 0 and 100. So never say proportion when you mean percentage, never say percentage when you mean proportion, and never say either when you mean frequency. The frequency is just the number of incidents. So if I collected 1,000 individuals and I found that the most frequent age is going to be age 34, that's a frequency measurement, and I might find 359 people are age 34. So that's the number of incidents, and that's going to be a frequency. So again, proportion between 0 and 1. Percentage, 0 and 100%. And frequency is going to be the number of incidents, the number of data points. We also have something called data transformation. And data transformation can make it easier to handle. Taking a proportion is a type of transformation. And it's fine so long as all of the data is going to be transformed. We'll get into that a little later. Next, how are we going to present it on a graph? There are a bunch of different ways we can graph things. Microsoft Excel will automatically give you a bar graph, and it is usually not the way you want it. So A bar graph is going to show some sort of ups or downs. So you can see the biggest bar is the highest proportion, highest percentage, highest frequency, whatever. A pie chart gives a share of the data, so you can kind of immediately focus in on what's the biggest share. And a scatter plot is going to give you something completely useless for what we're showing now, but it's going to give you data points given two axes. Now, for this, you need two separate axes to actually have the two separate values. So every data point needs an X and a Y value for a scatter plot. Honestly, you want to mess around with this. Look at your data, graph it, and don't just take the first thing Excel gives you. Nah. The first thing Excel gives is usually the worst thing Excel gives. Stay around for the good stuff. Present it in a pie chart. Does it look better? Does it look more scientific? Bar charts are cutest. Gunmetal gray, not blue. All right, what's the distribution of our data? So, D for distribution here. So the D for distribution is giving kind of a feel for the data overall. So this is a type of graph that shows proportions of a population. So this is specifically the IQ. So the IQ is a normal distribution. We'll get more into that later, but it's really the mean, the median, and the mode are all about the same. The mean IQ is 100. The median IQ is 100. The modal IQ is 100. So most people you will encounter are going to be within one standard deviation of an IQ of 100. What's the likelihood that randomly sampling a population, you're going to grab out someone who has an IQ over 145? Well, we won't grab them. They're too smart for that. No. It's 0.1. 0.1%. That's a percentage. So 1/10 of 1%. What's the likelihood? It's very rare. You're 99.9% likely to get someone who has an IQ below 145. If you were just like 3 people at random, I'm going to go to Fred Meyer and I'm just going to randomly snare 3 people. Is that going to be a good representative range? Probably not. The bigger the sample, the more representative it is of the distribution. And we can visualize a distribution not only by one of these curves, but by creating a histogram. This is a type of chart where you have one bar for each measure. So here we see a different distribution. So we see a normal distribution where the mean, the median, and the mode are the same. Here we have a histogram with a bar of each one, a very small bar. This kind of looks curvy from here. They can be left skewed or right skewed, and we'll see what the mode is too. So the left skewed are going to have, well, they're going to be pushed towards the left, right skewed pushed towards the right. And you can also have different modes. So we'll come back to this later with different distributions, but this is a single mode. A normal distribution has one hump. Something with 2 humps would be we call bimodal. More than 2, multimodal. We'll come back to that later, but you remember the term mode, meaning most common, it means there's more than one most common. All right. So I'm going to desire that we'll work on a histogram as a bit of some homework and try to build one of these using Microsoft Excel, installing the proper add-ins and building a histogram to show a distribution of a population. It's really just a series of boxes. If you were to connect all the peaks of those, it's going to make that kind of curve that we see over here. It's just connecting the peaks. Or think about putting more boxes in. It's kind of just like taking an integral of something if we've taken calculus. Bimodal versus unimodal. Symmetric, meaning both sides are the same, versus skewed, pushed one or the other. And also think about how long the tails are. So that's the sloping off. How long is that slope? It tells us something about the population. All right, next, think about transforming a bit. So normal distribution is useful for a lot of statistics. We like normal distributions. We like the mean, the median, the mode all being very close. We can use different data transformations, such as multiplying each one by 3 or taking the natural log of each number. And that's going to make a normal distribution out of one that didn't exist before. And this is what technically means to curve grades. If there's not a normal distribution, but we want a normal distribution, we're making a curve. It means most people are going to get a C. All right. So what about the variability? I've got a population. It has some traits. How variable is it? Well, there's 3 different measures we're going to look at here. There's the range. What's the biggest? What's the smallest? And what's the difference between them? How big is your range? Then there's something called the variance, and it gives a calculation there. I will not be expecting us to use that calculation in general, but what we're seeing is you see that x minus x bar is each sample's difference from the mean. So you take the sum of each sample's difference from the mean. So one sample is 9, the mean is 8, you have 1. One sample is 7, you have a mean of 8, you have 1. You have one sample is 1, you have a mean of 8, you got 7. You add all of those deviations up, you square it, that way it stays positive, and then you take the sum of all of those. It's a lot. So, yeah. And then you divide it by the number of samples minus 1. So that's the sample variance. Standard deviation is simply the square root of the sample variance. So, oh, and by the way, here I'm showing this these mu's and sigmas. Mu is the mean, and sigma is the standard deviation. We're using Greek terms when we're dealing with the whole population. It's different than the sample. So these mu's and sigmas on this little graph showing some old school memes and Hermione. That's what that means there. And that, by the way, is a normal distribution, normal curve. Okay, and then there's the standard error, which is, I'm going to flip past this. The standard error is usually what we use if we want graphs to look prettier, and it's the standard deviation divided by the square root of the number of samples. So for a large sample size, it's going to be a larger denominator, and that's going to be a smaller standard error. This is why it's a good thing to get a good large sample size and use standard error. Tiny error bars. Nice. So take a moment and look back on the different types of data. We're going to cover distributions a bit more later, but take a good look at the normal distribution, and you see how that curve has equal sized tails, and the mean, median, mode are the same. Take a refresher moment to look up mean, median, mode, and make sure that we all have the same, we're all on the same page there. And standard deviation number, we're not going to calculate it directly, but have an idea of what it represents. So that's the class for today. If we have any questions, feel free to hit me up and email me at least to ask questions, or if we're having in person, just feel free to come in person and ask me some questions. I'm always glad to talk about descriptive statistics.